Hello. The objective of this lecture is to introduce the different philosophical design approaches that are used in the design of civil and architectural engineering structures, and to provide some background about the reliability basis of the load and resistance factor design philosophy. Let's get started. There are many different approaches to structural design. Three primary ones are allowable stress design, load factor design, and load and resistance factor design. I would say that of those, allowable stress design was probably the oldest or one of the first approaches for structural design. And load and resistance factor design is probably the most prevalent at this point. There are other approaches that are available. You could design by plastic design, performance-based design, or using post-design evaluation. But I would consider those to be secondary to the primary methods that are shown here. We'll talk about those a little bit towards the end of this lecture. Okay, allowable stress design is probably the oldest, maybe the simplest of the methodologies that we'll talk about. And for safety, we have the equation that little f has to be less than or equal to f sub a. So little f is the stress in a member due to the applied loads. We would use a lowercase sigma in a lot of cases, but lowercase f is used because old typewriters didn't have Greek letters on them. And then the allowable stress is typically calculated by dividing a limiting stress, f sub y in this case, by a factor of safety. That limiting stress could be based on yielding, f sub y, could be based on fracture, f sub u, or it could be based on buckling, where you put an f critical in there, f sub cr. And the factors of safety would vary from anywhere between 1.5 to 5/3, all the way up to 2, or maybe even something higher than that, depending on the situation. In terms of bending moment, then the equation would be that the sum of the moments that are applied to the section divided by the section modulus must be less than or equal to the yield stress divided by 5/3. 5/3 is a common factor of safety in the design of steel structures. Allowable stress design doesn't recognize the different variabilities of the loads that are applied or the variability of the resistance that the members have. And that's a significant limitation to the use of allowable stress design. But I will say that allowable stress design is a simple method to use. And it has one advantage in that it doesn't matter whether you're looking at a member in a one-story CVS type of a building or whether you're looking at a member in a 100-story skyscraper. The stress that's in the member is going to be within the same range. It should be in the range of somewhere around 15 to 30 KSI. But the forces that you're using in those members, they could vary anywhere from, say, 50 kips all the way up to 500 or 5,000 kips. So working with stresses is a bit more intuitive to most people than working with forces. So that's one of the advantages of allowable stress design. And then the one specification that you might work with as a civil engineer that still uses allowable stress design is the railway specification. It's been the slowest to adopt more modern design approaches. Okay, and then the second one is load factor design. And for safety, we have to make sure that the sum of gamma times Q is less than or equal to R sub n. In this case, gamma is a load factor, Q is a member force due to the applied loads, and R sub n is a nominal member resistance. Okay, if we put that in terms of bending moment, what we do is we separate out the dead load moment, the live load moment, and we apply different load factors to those different actions, right? So the idea is that dead load is going to be more predictable than live load, for instance. And we would make sure that the sum of those moments is less than or equal to the moment capacity of the member. Now, load factor design is an improvement over allowable stress design, but it doesn't recognize the variability of the loads and the resistances at the same time. It still recognizes them separately, which is a shortcoming. None of our major specifications use load factor design at this point. The last one really to do so was the old ASCE standard specification, which was based on allowable stress design, but it did have a load factor design alternate in one of the appendices. Finally, we get to the load and resistance factor design philosophy. And for safety, the equation is the sum of gamma times Q must be less than or equal to phi times R sub n, where Q is a member force due to the applied loads, gamma is a load factor, R sub n is the nominal member resistance, and phi is a resistance factor. The advantage of load and resistance factor design is that it provides a more uniform, systematic, and rational approach to the selection of load factors and resistance factors than LFD does. And just about all of the major design specifications that you're going to use for civil and architectural engineering structures are based on LRFD. So here we're showing the concrete design spec, ACI 318, the main steel design specification, AISC 360, and the AASHTO LRFD bridge design specification. Okay, to illustrate the principles of load and resistance factor design, let's take a sample set of data. Suppose that we take 100 students and we put them all on scales and we measure their weights. Okay, what we're going to do is we're going to bin the data that we get. So instead of recording everybody's weight out to 4 significant figures, we're just going to check the boxes like this. So we say that there's one person that has a weight that's between 86 and 95 pounds. There are 2 people that weigh between 105 and 115 pounds, et cetera, et cetera. On average, the students weigh 180 pounds, and the standard deviation would be 38 pounds. Okay, we can represent that data a little bit differently. We'll plot it first as a histogram, where each one of these bars represents the number of instances in a particular group. So the one student that weighed between 86 and 95 pounds is in this bar here. The 2 students that weighed between 105 and 115 pounds is right there. So this is called a histogram, and it represents graphically the data, the binned data that we had on the previous slide. So this is more useful, but a more useful yet way of presenting this data is to fit a curve to it, and we can call that a probability density function of Q. So that is a continuous curve. It's not a perfect representation of the data, but it is a statistically useful representation of the data. So then we make the histogram go away, and we work with this bell-shaped curve as a representation of the weight of 100 students that are in a hypothetical class. Okay, next, suppose that we want to measure the strength of 100 ropes. Maybe this class is going rock climbing. So we take 100 different ropes into our laboratory, put them in a test machine, and we pull on them until they break. And again, we bin the data. So we have one rope that failed somewhere between 246 and 255 pounds. And at the other end of the spectrum, we have one rope that failed between 395 and 405 pounds. So on average, we have a strength of 320 pounds for our ropes, and the standard deviation of the strength is 28 pounds. So what we'll do now is plot that rope strength as a histogram, much like we did before. And one thing that you might note, it's not by mistake, is that the curve here is a little bit tighter, right? And it has a peak that is a bit more sharp. And that's characteristic when you look at the data of a strength or a resistance of a component relative to the data associated with loads. What that means is that the strength is a bit more predictable, less variable. And if you look at the load curve that was a bit wider, that means that it is a bit more variable. It has it's a little bit more challenging to predict, for example. Anyways, what we'll do is we'll take this histogram for resistance. We'll fit a probability density function to it, just like we did for strength. And then we'll work with that probability density function instead of working with the histogram. Okay, so the next step is to plot both the probability density function for the load, Q, next to the probability density function for the resistance, R. And here you can really see the different shapes of these curves. They both PDFs represent 100 samples, but the PDF for Q is a little bit wider than the PDF for R, indicating that the load data is a bit more variable than the resistance data. So if we look at the averages here, On average, the students weigh about 180 pounds each, and on average, the ropes have a strength of 320 pounds. So if we take this class of 100 students rock climbing and everybody just grabs a random rope, then on average, everybody should be fine, right? The strength is on average, 140 pounds stronger than the weight that should be applied to them. However, it is possible for the heaviest student in the class to select the rope that has the least strength. And in that case, you might have a load that is greater than the strength. And that's represented by the overlap of the two curves. And that region that's highlighted in red now represents the possibility for there to be a failure. In other words, probably everybody is going to be safe, but it is statistically possible for the heaviest person in the class to grab the weakest rope, and that would represent a statistically small chance of failure. So the trick for us is to figure out how to make that probability of failure small enough that we can tolerate it as a society. So what we're going to do on this slide is plot a single probability density function, the PDF of R minus Q. So in this case, when R minus Q is positive, that means that R is greater than Q. The resistance is greater than our load, and everything is safe. On the other hand, when R minus Q is negative, that means that Q is larger than R. That means that the load is larger than the resistance, and that correlates to a structural failure. So if we look at some of the statistics associated with this curve, we have the mean value that goes through the peak of the curve, and we can define some quantities down here on the axis. The value sigma is a standard deviation of the data that we have, R minus Q. And then the value beta is referred to as a reliability index. So what we can do is we can calculate sigma, the standard deviation of our data, and then we can set beta so that that's the number of standard deviations of the mean away from the vertical axis. By setting beta as our independent design parameter, we can control the probability of failure that we would have for our structure or for our components. Now, setting a value of beta is fundamentally a more rational approach to the design of structures than setting a value of the factor of safety, for example. Okay, this slide gives an indication of what the standard deviation is for a normal probability distribution. So if we look at this means that, let's see, one standard deviation of data includes 68.2% of the data, and that would mean that we were excluding 15.9% below. If we took instead and looked at two standard deviations of data, that would include 97.7%. And that would mean that 2.28% of the data would be excluded below that value. So what this correlates to is we can develop a relationship between the reliability index beta and the probability of failure, P sub F. So if we set beta equal to 1, that would mean that we would have a probability of failure of 15.9%. On the other hand, if we set beta equal to 3.5, then we would have a probability of failure of 0.0233%. So the trick for us as structural engineers is to balance the cost of the structure with the probability of failure of the structure, right? If cost was no issue, then we would set beta equal to something ridiculous like 10, and there would be almost zero chance of failure. But the problem with that is that you would end up with columns in CVS type buildings that are 3 feet in diameter, and it's just not practical. We can spend millions and millions of dollars for safety, but we do have to balance at some point the cost of the structure with the safety associated with that structure. So if you dig into the codes and the specifications, it's challenging to figure out what the value of beta is that each are based on. This slide shows some target reliabilities for performance-based design that are included in the ASCE 7 standard. So this isn't directly related to load and resistance factor design, but one might infer that if these are the target reliabilities for performance-based design, that the values that are used for load and resistance factor design must be similar. And I'm going to at least go with that inference. So what's shown here on the left are different types of failures that you might expect or might guard against in the design of the structure. So on the first line, you have a failure that is not sudden and does not lead to widespread damage. On the second line, you have one that's a failure that's either sudden or leads to widespread damage in the structure. And then in the third row, you have a failure that is sudden and results in widespread collapse. So the idea there is that you go from the most desirable type of failure, the one with the lowest consequences, down to the third row where you have the least desirable type of failure, one where you have no warning and it's going to cause almost a total collapse of the structure. So we want to guard against that last type of failure more than we need to for the first type of failure. If it's a localized failure, something that doesn't happen very fast and doesn't lead to a collapse of the structure, we don't need to guard against it as much. If it's going to lead to a total collapse of the structure, then we need to guard against it more. Then also we're looking at the risk categories here, right? So these are buildings in risk categories 1 through 4, where 4 is an essential facility, where 2 is our office building, 1 is a grain silo, right? So if we're looking at a hospital structure, we want to make sure that when we're looking at types of failures that are going to lead to collapse of the structure, we're going to use a higher value of beta, 4.5. If we're looking at an office building where we are looking at just the failure of one member, a localized type of failure, then maybe we could get by with a beta value equal to 3.0. So this slide shows the probabilities of failure associated with each of the reliability indices that were on the previous slide. Now, these probabilities of failure have been annualized, meaning that they are probability of failure for each year. Now, look at how small some of these values are. For example, if we look at a category 2 building and look at a localized failure, then we end up with a 0.003% chance of failure in any given year. On the other hand, if we look at a category 2 building and look at a widespread failure or a collapse, then we're looking at a probability of failure that is 0.00007% chance of failure in any given year. So that's pretty small. And then if we look at a category 4 building, we're dealing with a probability of failure that's even smaller. I think I got this right. 0.00001% chance of failure in any year. Now, it bears mentioning that each these probabilities of failure and the reliability indices on the previous slide don't include things like earthquakes, tsunamis, or extraordinary events. Okay, the table on this slide shows the target reliabilities for earthquake events. And so this is for a maximum considered earthquake, which is basically an earthquake that's has a mean recurrence interval of 2,500 years. And we'll come back and talk about that at the end of this lecture, but basically it's the mother of all earthquakes. So if you look at the different categories of buildings for risk category 1 and 2 building, for a non-critical member, we're looking at a 25% chance of failure per event. If we look at a risk category 4 building, for instance, we're looking at a chance of failure or collapse of the building of 2.5% per earthquake or per maximum considered earthquake. So these are a lot higher, but they're still relatively small. And it just goes to the fundamental philosophy of design in that when we look at performance of a building on a day-to-day basis, we shouldn't have any buildings failing under normal snow loads, rain loads, live dead loads, or even under routine wind events. But we're willing to tolerate the failure of a significant number of buildings under earthquakes, right? A maximum considered earthquake. Now, why is that? Well, two things, really. I mean, this is a maximum considered earthquake, so it's an earthquake that's going to occur every 2,500 years. So the odds of it occurring during the life of the structure are fairly small. Moreover, it's again a balance between cost and consequences, right? If we designed every building to resist an earthquake that probably won't ever happen, then the cost of the structures would just be so high as to be prohibitive. All right. So when it comes down to this, why is load and resistance factor design better than allowable stress design? Well, fundamentally, there's a misconception that a lot of people have, or at least they used to have when LRFD was introduced. The misconception is that LRFD will provide a cheaper design. That's what people thought was the driving reason to go to LRFD. The truth, the truth is that LRFD will result in a more uniform level of safety in the design. If you tell somebody that you're using a factor of safety of 5/3 or 2.0, you really don't have any idea what the probability of failure associated with those factors of safety is or are. On the other hand, if you tell somebody you're using load factors and resistance factors that are based on a reliability index of 4.5, you can trace back, at least loosely, to the probability of failure associated with that. So that's why LRFD is superior in most people's opinions to allowable stress design. As a measure of that, some researchers, Chen and Duan, went and looked at the reliability inherent in bridges that were designed using allowable stress design approaches or load factor design approaches. And they found that the inherent reliability was somewhat variable, ranged from between 1.5 all the way up to about 4.5. And it was also a function of the span length of the structure. When they went back and looked at the reliability of bridges that were designed using load and resistance factor design, they found that the reliability of the bridges was much more uniform. The bars aren't nearly as high, and it was much more evenly distributed over the span lengths for the structures. So you got a more uniform design, a more balanced level of safety in those structures using LRFD than you did using ASD. All right. Now, so some of the other approaches that people have used or can use, plastic design is probably an almost an outdated approach now. It's still used in seismic design to some extent. It's basically a method of designing beams and frames to develop a collapse mechanism in the structure. And the approach is known as plastic design because of the stress strain curve for steel. So if we look at this region of the stress strain curve, that's the elastic region. And if we get past the yield point into that region there, that's the plastic region of the steel, the yield plateau. So when we design for plastic design, then our structures are getting into that plastic region of the stress strain curve. So that's why it's called plastic design. Performance-based design is something that's just starting to come into vogue now. And the idea with performance-based design is that rather than going to a specification where it says that each member has to satisfy the sum of gamma q less than or equal to phi times r sub n, you go in and set different design criteria for the structure. Maybe as an owner, you would say that under a normal, let's say under an earthquake that has 5.5 on the Richter scale, I don't want any more than $400,000 worth of damage to my structure. Something like that. So what you do is you develop objective performance criteria that might include different damage states for the structural elements, for the architectural elements like windows and lighting and things like that, mechanical, and possible damage to the contents of the structure. And after you develop those criteria, you figure out what is acceptable, what is not acceptable, and you try and size the structural elements or the performance of the system based on that criteria. Okay, and the last one that I'll mention here is called post-design evaluation. And this is basically a process that somebody that already has a building would use to assess it for risk associated with current design specifications. So suppose you're an owner of a building that was constructed back in the 1970s. The design specifications back then aren't as weren't as robust as they are now. We didn't have as good an understanding of seismic behavior then as we do now. So maybe now you would want to have your 1970s structure evaluated using 2020 technology. And what you would do is a post-design evaluation of that structure. All right, I'm going to close this lecture by talking about some more statistics associated with loads. And I'm going to define 3 or 4 terms. The first one is an arbitrary point in time loading, an APTL. This is the load that can be expected to be on a member at any arbitrary point in time. In other words, it's the average magnitude of the load on any random day in the life of the structure. The next term that we define is the maximum lifetime load. And this is the largest load that could be expected on a structure or in a member of a structure during the life of the structure. Now, as far as ASCE is concerned, buildings are designed for a 50-year service life. Now, certainly there are a lot of buildings out there that are older than 50 years. And if you look at bridges, AASHTO defines a service life as 75 years. But anyways, we define 50 years as our life. So a maximum lifetime load is the maximum load that can be expected over a 50-year period. And then we define the term the maximum considered load, or the MCL. This is the largest load that could be expected ever. And forever in this context is defined as a period of 2,500 years. All right, now the last term that I'll define is the mean recurrence interval. And this is the average time between occurrences of a random variable. So let's suppose that we define our random event as an earthquake with a magnitude 8. So that's magnitude 8 on the Richter scale. What is how long is it going to be between each of those events at a given point? So that would be the mean recurrence interval. If you think it's going to be, say, 1,500 years in between magnitude 8 earthquakes in any given location, then the mean recurrence interval would be 1,500 years. So that goes back to the idea of a 50-year storm or a 100-year storm, right? So that's what a mean recurrence interval is. Now, the probability that an MRI value will be exceeded in any occurrence can be calculated as 1 over the MRI, 1 over the mean recurrence interval. So for a maximum lifetime load, you would say 1 over 50 years is 0.02 or 2%. So that means that a maximum lifetime load has a 2% chance of being exceeded each year. So if we talk about a 50-year rain or a 50-year storm, then in any given year, there's a 2% chance that that 50-year storm will be exceeded. On the other hand, if we're talking about a maximum considered load, then the probability that that's going to be exceeded is going to be 1 over 2,500 or 0.0004 or 0.04%. That means that the maximum considered load has a 0.04% chance of being exceeded each year. Or another way of looking at that is that this is roughly a 2% chance of being exceeded in 50 years. So when we look at the design of our structures, we talk about a 50-year mean recurrence interval on some loads. We talk about a 2,500-year mean recurrence interval on other loads. And we talk about the arbitrary point in time value of still other loads. So if we want to map between these, we could say that the maximum lifetime load is approximately equal to 1.6 times the arbitrary point in time load. Or going the other way, we could say the arbitrary point in time load is about 2/3 of the maximum lifetime load. On the other hand, the maximum considered load is about 1.6 times the maximum lifetime load, or the maximum lifetime load is about 2/3 of the maximum considered load. Now, yes, this is rough math, but it's statistics anyway, so everything is just approximate anyways. I suppose if I said that to a statistician, they would probably cringe, but be that as it may. Okay, so if we look at the weight of 100 students again, recall that we had an average value of 180 pounds. So if we were designing, we would say that the arbitrary point in time load is basically the average value of our student weight, or about 180 pounds. If we want to calculate the maximum lifetime load, then that would be about 288 pounds. So remember, the largest student, or the heaviest student in the room, I think weighed somewhere around 300 and some pounds. So the maximum considered load would be 460 pounds. So that gives you an indication of what these three load levels are like. So you have the arbitrary point in time load, the maximum lifetime load, and the maximum considered loads. So when we look at the loads as ASCE 7 presents them, we have these main loads: dead, live, roof live. We have the snow load, the rain load, the wind load, and the earthquake loads. When you calculate these loads per ASCE 7 standards, the first 4 or 5 are calculated as arbitrary point in time loads. So if we calculate the live load or the dead load that's on the structure, you're typically calculating the load levels that you would expect on any given day. On the other hand, when you look at the wind load or the earthquake load that you're calculating the maximum lifetime load that you would expect for your structure. So that's important to bear in mind when we move into our next conversation about load combinations. The basic load combinations that are in the ASCE 7 standard are shown here. The first combination, shown as 1.4 times the dead load, is included to address long span structures or structures that have a high dead load to live load ratio. The second combination is the basic design load combination that includes dead load and live load at their maximum lifetime levels, along with the environmental roof loads, L sub R, S, or R, at their arbitrary point in time levels. The third load combination reverses that, considering the environmental roof loads at their maximum lifetime level, acting concurrently with the transient loads acting at their arbitrary point in time level. Next, we have load combinations 4 and 5 that address wind. And then finally, we have load combinations 6 and 7 that address the seismic loads. If we look at some of the details associated with these 7 load combinations, we'll find in the exceptions included in the ASCE 7 standard that the load factor on L in combinations 3, 4, and 6 is permitted to be taken as 0.5 for all occupancies in which the unreduced live load is less than or equal to 100 pounds per square foot. The live load levels that we design for are often in the range of 40 to 70 pounds per square foot, occasionally up to 100 pounds per square foot. It's only in rare cases that the design live load is higher than 100 pounds per square foot, so in many cases we can design for 0.5 times L in our load combinations. We also have to consider the possibility that in some cases it can be more critical if one or more of the transient loads or environmental loads aren't acting on the structure. Let's take this 2-span beam for example. We have a uniformly distributed dead load, and that's going to lead to the case where we have positive moment near the middle of each of the 2 spans and negative moment over the center support. Now suppose that we're designing for a live load that consists of 2 point loads acting in each of the 2 spans. If we have all 4 of those point loads acting on the beam, that would result in the maximum negative moment over the center support. But that isn't the most critical case when you consider positive moment. If you were to design for just the 2 live loads acting in the first span, that would lead to a larger positive moment in the first span than all 4 live loads acting together. Additionally, considering only the 2 live loads in the first span would result in a negative moment in the second span. Similarly, if you were to design for just the 2 loads in the second span, that would actually lead to a larger positive moment in the second span than if all 4 live loads were acting together, and might result in a negative moment in the first span as well. So the takeaway here is that you have to consider different permutations of transient and environmental loads acting on the structure. Sometimes the case of some or all of the transient loads not acting is actually the critical case. There are several other permutations to these load combinations that also need to be considered. For example, in load combinations 4, 5, 6, and 7, we have the plus or minus sign that indicates the directionality associated with the wind load and the horizontal earthquake loads. In load combination number 3, you'll see that we have 0.5 times L or 0.5 times W. And finally, in load combinations 2, 3, and 4, we need to consider either the roof live load or the snow load or the rain load. One way of simplifying this a bit is if we consider the roof loading as a single variable, defining 0.5 times L sub r or 0.3 times S or 0.5 times R as the arbitrary point in time roof loading R sub APT, and defining 1.6 times L sub r or 1.0 times S or 1.6 times R as the maximum lifetime level roof loading, R sub MLL. When we make that modification, the load combinations look like this, where we use R in place of the roof loads in combinations 2, 3, and 4, using R sub APT to represent the roof loading at its arbitrary point in time level, and using R sub MLL to represent the roof loading at its maximum lifetime level. This can be a bit confusing at first since we're using R to denote the rain load in some cases, and then we're using R to denote the roof loading in other cases. But after you work through a few problems, the utility of this approach should become apparent. Finally, when we consider all the different variations of the load combinations, the possibility that some transient loads may not be acting, and consider the directionality of the wind and the seismic loads, we are left with these 27 permutations of the original 7 load combinations. Before I close out this slideshow, I wanted to present this slide, which I borrowed from a project management company. I've seen this image or this figure in a number of different forms over the years, but this was a nice clean version, so I went ahead and borrowed it with a reference there at the bottom. And it gives a visual indication of an approach to risk management, which considers the consequences of an event and the likelihood that the event will even occur. So in all 4 different cases here, you can see an individual jumping over a pit. In the lower left case, you have a low likelihood that the individual is going to fall into the pit, and the consequences are fairly minimal as well. Even if he doesn't make it when he tries to jump over the pit, all he does is get his feet wet, so no big deal, right? And on the other hand, on the upper right-hand corner, you see the individual trying to jump the pit, but it's a longer jump this time. So the likelihood that he's going to encounter the event, the likelihood that he's going to fall into the pit is much higher. And the impact is also much worse as well because the pit is deeper and there are sharp, pointy things at the bottom. So if he falls into the pit, he's more likely to be injured than he would have been in the lower left or the lower right case. So you can consider both of these different variables when you consider the assessment of risk in a structural engineering context as well. So think about what happens if a beam fails, for example. That might lead to the collapse of one floor, or that might lead to the collapse of a bay of framing or something like that. Whereas if a column fails, that could lead to a progressive collapse and bring down a building. So we consider assessment of risk in structures kind of like that as well. So the likelihood of a failure is relatively small, and in the case of a beam, the consequences of that failure are relatively limited. But if we consider the consequences of a failure of a column or something that's in the load path of a structurally determinate system, then that could bring down the entire system. So the consequences of that failure are rather severe. Okay. Okay, that brings us to the end of this lecture. Hopefully by now you understand that the 3 primary methods of design are allowable stress design, load factor design, and load and resistance factor design. Also, I hope you have at least a loose understanding of the reliability basis of LRFD and understand why many people consider it to be the preferred method of those 3. There's a lot more to be learned about reliability. We offer a class at the undergraduate level, and it's called CVE 3003, Reliability, and it's required for all of our civil engineering students and is open to our architectural engineering students to take as well. We used to have an offering at the graduate level, but we haven't had the opportunity to offer that class in several years. Anyways, next lecture is on load combinations. So thanks.